All right, welcome back to another episode of Scientifically Simple. My name is Brandon. I'm joined today by Mo, and we have something very special prepared. In fact, it is so special I have no idea what it is. So, without further ado, Mr. Mo, take it away.
Thank you, Brandon. Our clip today would be talking about the evolution of chemistry, thermodynamics, and reactions. So, for a start, we are going to be talking about a quick recap on previous thermodynamic clips, thermodynamics and chemistry evolution, calorimetry, and chemical reactions, and as usual, we are going to be providing a summary at the end of our discussion. So, chemical thermodynamics, for a recap, we mentioned that the state function is a path independent, while a path function is path dependent. Enthalpy, internal energy, and entropy are state functions. Pressures, temperature, volume are interdependent. Specifying two of them will determine the third, and that's how we learned in our equation of state episode. Willard-Gibbs played a monumental role in transforming thermodynamics to play a global role in physics and chemistry, and it's going to be specifically highlighted why especially Gibbs became a center stage between chemistry and thermodynamics during this episode. The global demand for chemical revolution paved the way for thermodynamics to go beyond the heat engines. So, as we know, chemical engineering thermodynamics is a study of interrelations between heat, work, and chemical reactions, or physical changes of a state within confines of the laws of thermodynamics. The history of chemistry is intertwined with the history of thermodynamics, especially through the work of Gibbs, as we are going to be highlighting. So before digging into chemical equilibria right away, I thought we should have a snapshot on history of chemistry and how it evolved across the human civilization. It will cross path eventually with thermodynamics. From the four elements of fire, water, air, and earth to thermochemistry, analytical, organic chemistry, isomerism, polymer chemistry, and fluorescence, chemistry as thermodynamics evolved as a human civilization developed across the centuries. And eventually chemistry will be merging with thermodynamics, as that was critical for the emergence of the chemical industry.
Now wait a minute, Mohammed, I need to correct
you.
Thermodynamics does not apply to polymers.
Oh, did you have to say that right now? Did you, wait, dude, are we still recording? Oh my god, you had to throw it just now.
I'm deciding whether I'm going to leave
mood.
that in. We'll see in editing.
No, don't do that. Don't destroy the whole moment.
Excellent.
I was preparing for this. So starting with the pre-17th century, in 450 BC, Empedocles asserts that all things are composed of four primal roots, which is earth, air, fire, and water, whereby two active and opposing cosmic forces, love and strife, act upon these elements, combining and separating them into infinitely varied forms. In 440 BC, Democritus proposed the idea of an atom, an indivisible particle that all matter is made of. And just think about it. That's a person in 440 BC coming up with that concept. Just wanted to highlight that because it's very important to be just not underestimating how smart people were back then. Between 850 to 900, Jabir ibn Hayyan, also known as Jibr, introduces the systematic classification of chemical substances and provided instruction for deriving an organic compound, which was mainly ammonium chloride, from organic substance using plants, blood, and hair through a chemical means. In year 1900, Abu Bakr al-Razi, or Rhazes in Latin, he was a Persian alchemist, conducted experiments with distillation, again of ammonium chloride, hydrated sulfates of various metals. That was representing the first step in a long process that would eventually lead to the 13th century discovery of mineral acids. So that's where mineral acids have been introduced. In 1250, Taddeo Alderotti described a method for concentrating ethanol involving repeated distillation. That was the first person to be actually working about.
That is really cool.
How you can distill alcohol through a water-cooled still, by which ethanol purity was achieved at 90%. He was able to achieve a 90% purity. So he understood that distillation is capable of doing this in 1250. In 1260, in 1260, Saint Albertus Magnus discovers arsenic and silver nitrate. 1267, Roger Bacon proposes an early form of scientific method. And in 1530, Paracelsus develops the study of iatrochemistry, which is might sound strange. That was a subdiscipline of alchemy dedicated to extending of life. So that was, in modern terminology, that was the start of pharmaceutical industry.
Yeah.
It was also claimed. Yep. It was also claimed. Nobody exactly knows, but was also claimed he was the first person to be using the word chemistry. In 1597, Andreas published Alchemia, and it was the first prototype chemistry handbook. Now, moving to the 17th century, 1605, Sir Francis Bacon published The Professions and Advancement of Learning, which contains a description of what would later be known as scientific method. 1605, Michael, I am always struggling with that last name.
Just make up something. Nobody's going to double check you.
I'm gonna struggle with majority of the names. Published the alchemical treatise A New Light of Alchemy, which proposed the existence of food of life. Michael was the first person to basically pinpoint as something called food of life within air, which was known as oxygen later on. He didn't know it as oxygen, but basically he was going to the aerobic metabolism. He was saying part of the energy in us coming from air, but he didn't know it is oxygen. In 1615, John Bigwin published the Tyrosinium Chemicum, an early chemistry textbook, and it draws the first ever chemical equation. That's the first time a chemical equation was written. In 1648, Jean-Baptiste van Helmont published an early version of the law of conservation of mass. So just look at this now and just connect it with what we have discussed in previous clips. In 1661, a year before publishing the Boyle's Law, Robert Boyle published The Skeptical Chemist, a treatise on the extinction between chemistry and alchemy. It contains some of the earliest modern ideas of atoms, molecules, and chemical reactions, and hence that marked the beginning of the history of modern chemistry. That's basically in 1662 he come up with Boyle's Law for the gas. Now we are going to 18th century, 1754. Joseph Black isolated carbon dioxide, which he called fixed air, and he was the first person to formulate the concept of latent heat to explain thermochemistry and the phase changes. In 1757, Louis Claude Cadet, while investigating arsenic compounds, he created something called Cadet's fuming liquid, and that was discovered later on to be cacodyl oxide, considered to be the first synthetic organometallic compound. 1766, Henry Cavendish discovers my favorite molecule, hydrogen, as a colorless, odorless gas that burns and can form an explosive mixture with air. That's 1766. 1774, Carl Wilhelm Scheele and Joseph Priestley independently isolate oxygen. So, it was known that it's a food of life, but finally those guys were able to isolate the oxygen. Now, 1778, the father of modern chemistry, Antoine, we have spoken about him several times during the thermodynamic clips. He did three crazy important three steps during that time. He recognized and named oxygen, and he recognized how important it is to combustion. So he basically defined the oxygen as a central role molecule in combustion. Number two, he published the method de nomenclature chimique. That was the first modern system of chemical nomenclature. Number three, he published Traité élémentaire de chimie. Just pardon my French. That's just the French book that he produced. The first modern chemistry textbook. It's a complete survey of, at the time, modern chemistry, including the first concise definition of law of conservation of mass, and thus also represent the founding discipline of stoichiometry or quantitative chemical analysis. You can see now how everything are pretty much brick by brick is being built as we move forward. In 1797, Joseph Proust proposes the law of definite proportions, which states that elements always combine in a small whole number ratios to form compounds. So there is no half oxygen, there is no quarter nitrogen. You know, as we write something, it's like N2O5, not like N half quarter or something. So that's that's where
it's crazy
in
to think about. That
1797.
was 200 years ago, and they didn't have anything near like the equipment we have today. And they are making profound, accurate conclusions. That's insane.
It's fascinating. Yep.
I can't fathom it.
It's fascinating. It's really just like it just goes to show how deep the human intellect can.
And we can't even go back to the moon.
Or like if you you need the motivation for it. That's the critical part. You need the motivation for it. And so moving to the 19th century, we are going to spend some time there. In 1800, Alessandro Volta devises the first chemical battery, thereby founding the discipline of electrochemistry. If you're called a frog, so that's the dude. In 1803, John Dalton proposes Dalton's law, which describes the relationship between the components and mixture of gases and relative pressure each contributes to the overall mixture. Pretty much, that's the guy that's related the mole fraction to the partial pressure of the gas. 1808, John Jacob proposes modern chemical symbols and notion, and he was the first one to introduce the concept of relative atomic weight to carbon. Remember, that's how atomic weight was built. In 1825, Frederick Wohler and Justus von Liebig performed the first confirmed discovery and explanation of isomers. Working with cyanic acid and fulminic acid, they correctly deduced the isomerism was caused by different arrangements of atoms within a molecular structure. It just is seriously the amount of intellect, the amount of
it's just crazy,
like, it's just it's very impressive. 1827, William Prout classifies biomolecules. This is 1827. William Prout classifies the biochemicals into modern groupings of carbohydrates, protein, and lipids. Hence, biochemistry. This is now the realm of, the first steps to biochemistry. 1827, Frederick Wohler synthesizes urea, thereby establishing that organic compounds could be produced from inorganic starting materials, disapproving the theory of vitalism. If you don't know what theory of vitalism, pretty much like at its core, anything in biology can be explained by something non-biological. So pretty much by getting something that's organic and is part of biology, for example, he disproved that you can't get anything organic from inorganic chemistry, for example. So that vitalism is going to get the first hit. It's going to get another hit later on as we speak. Frederick Wohler, for the second time, 1832, along with Justus von Liebig, discover and explain the functional groups and radicals in relation to organic chemistry. In 1840, German Hess, he proposes the Hess's law, an early statement of conservation of energy, which established that the energy changes in a chemical process depend only on the states of the starting and product materials and not on the specific pathway taken between the two states, which is going to come later on to be known as enthalpy of reaction. He did not say it's an enthalpy of reaction. He pretty much said, we have, here is the energy state of the reactants, here is the energy state of the products. Irrespective of how to go from A to B, it's going to be constant irrespective. That's going to come later on to be known as the enthalpy of formation. 1847, Hermann Kolbe obtains acetic acid from completely inorganic sources. This is the second strike for further disapproving vitalism. Now, we are still in the 19th century. We're going to stay there for a while. 1849, Louis Pasteur, the dude who, by the way, came up with the milk pasteurization, discovers that the racemic from tartaric acid is a mixture of two compounds, thus clarifying the nature of optical rotation and advancing the field of stereochemistry. 1849. 1849.
You're right.
And just imagine the equipment that he didn't have. Yeah, so 1852, August Beer, who you can't tell from his last name what he was famous for. Yeah, proposes Beer's law, which explains the relationship between the composition of a mixture and the amount of light it will absorb. He establishes the analytical technique known as spectrophotometry. Not bad for a guy who invented the beer. 1855. Benjamin Silliman Jr. pioneers the method of petroleum cracking, which makes the entire modern petrochemical industry possible. 1855. 1856. William Henry Perkin synthesized Perkin's move, the first synthetic dye, created as an accident. He created that dye by an accident, but became, byproduct of, he was trying to make quinine from coal tar, and he ended up making the dye. This discovery is the foundation of the dye industry.
That's very cool.
Synthesis industry. And it's outstanding. 1857, Frederick August Kukuli, and just keep that name in mind, proposes that carbon is tetravalent, forming 4 chemical bonds. He's going to come back later. We're not done with him yet, by the way. 1859 to 1860, Gustav Kirchhoff and Robert Bunsen lay the foundation of spectroscopy as a means of chemical analysis, which lead to the discovery of cesium and rubidium. 1860, Cannizzaro, resurrecting Avogadro's ideas regarding diatomic molecules, compiles the table of atomic weights and presents it to the 1860 Karlsruhe Congress, ending the decades of conflicting atomic weights and molecular formulas and paving the way for Mendeleev's discovery of periodic table. 1862, Alexander Parkes exhibit Parkinson, one of the earliest synthetic polymers, at the International Exhibition in London. This discovery formed the foundation of modern plastic industry. That happened in 1862. I'm telling you, you're going to be seeing a lot of cool stuff in this. 1864, John Newlands proposes the law of octaves. I don't know if you remember it or not. A precursor to the periodic law. Pretty much like the octaves, which is the outer shell. If it's filled with 8 electrons, it's going to be inert. If it's less than that, it's going to share. So that's pretty much John Newland. And of course, we know it's not 100% accurate. And very, very long century, the 19th century. We are still in it. 1864, Lothar Meyer develops an early version of the periodic table with 28 elements organized by valence. 1865, John Loschmidt determines exact number of molecules in a mole. This is the guy that come up with the mole, as you know, from Avogadro's number. And that's basically, how Avogadro's number is known as this gigantic 6 multiplied by 10 to the power 23 molecules. That's the mole. 1865, Frederick August Kekule. I told you he will be back. Based on partially on the work of Loschmidt and others, he establishes the structure of benzene, the aromatic compound, as a 6-carbon ring with alternating
cool.
single and double bond. That's the guy that discovers going to be planar and there's going to be a resonance in the aromatic ring. 1865, Adolf von Baeyer begins work on indigo dye, which was a milestone in modern industrial organic chemistry and revolutionized further the dye industry. 1869, I'm pretty sure you know that name, Dmitry Mendeleev, publishes the first modern periodic table with the 66 known elements organized by atomic weights. The strength of that table was its ability to accurately predict the properties of as yet unknown elements. So back then he was able to discover some element that hasn't been discovered yet. In 1876, our man, Willard Gibbs, publishes On the Equilibrium of Heterogeneous Substance, a compilation of his work on thermodynamics and physical chemistry, which lays out the concept of free energy to explain the physical basis of chemical equilibria, and that's where Gibbs fits at that junction between chemistry and thermodynamics. 1877, your buddy, Ludwig Boltzmann, establishes statistical derivations of many important physical and chemical concepts, including entropy and distributions of molecular velocities in the gas phase. And that, I know, it's we are still in the 19th century. That's why that century is awesome. 1880, and by the way, speaking of Boltzmann, we are going to be really going down with that guy in the upcoming kind of episode when we're talking about the third law of thermodynamics and statistical mechanics. It's going to be a cornerstone that's going to be showing how classical thermodynamics and quantum mechanics, it wasn't a step change. There was actually way more spectrum continuity between understanding that to go to that one. He was a fundamental role there. 1883, our my favorite guy in kinetics, Arrhenius, develops ion theory to explain conductivity of electrolytes. 1884, Jacob Van Hoff publishes Dynamique Chimique, a seminal study of chemical kinetics. 1880s, we're talking about kinetics. And we are still in the century that never ends. 1884, Hermann Emil Fischer proposes the structure of purine, a key structure in many biochemicals, which he later synthesized in 1898. He also begins work on the chemistry of glucose and related sugars. You can see proteins and everything is getting pretty much dicey there. Everybody's understanding, oxygen, carbohydrates, glucose, etc. 1884, Le Chatelier has been addressed in our last clips, develops the Le Chatelier principle, which explains the response of dynamic chemical equilibria to external stresses. 1893, Alfred Werner discovers the octahedral structure of cobalt complexes, thus establishing the field of coordination chemistry. It's almost all the chemistry branches coming up in that century. 1898, William Ramsay, and that's why we have the picture up there on top, discovers the noble gases, which fills a large and unexpected gap in the periodic table and led to models of chemical bonding.